Welcome back. In this video, we're going to take a look at more techniques of evaluating limits. A lot of this is going to be the same as we looked at it in our first video. We're going to have some special properties. You might need to pause the video along the way to write down these properties, but we're going to be taking a look at some of the special properties that are associated with limits. That will just try to help you. Some of them are common sense, some of them may take a little bit more work, but we're still going to be evaluating limits algebraically, just like we did in our first one. On our first property, we have the limit as x approaches a of a constant value. And on that constant value, that's going to be something like if you had the equation, let's say we just had the equation y equals 2. Y equals 2 is a horizontal line at 2. So no matter what the x value is, the y value is always 2. So let's say a is here. Well, if I approach a from this way, or a from this way, I'm still at 2. No big deal. If I have the limit as x approaches a of x, that's just going to be the identity function. That's going to be the a value. Remember, this is just a line that bisects the first and the third quadrant. So our identity function looks something like this. And again, let's say a is here. Well, this point right here is going to be at a. So that's going to be a. The third one just says if you have a polynomial function, if I have f of x plus or minus g of x, that I can separate them out individually and then just add them together. And the fourth one just says that if you're going to multiply them, you can evaluate them individually first and then go ahead and multiply them. A lot of this we already did intuitively. Number 5, same thing, but it's division. Number 6, we can pull a constant out front. That's often very helpful. And number 7, if I'm trying to evaluate a limit as of what we call a exponential function, or where we have the base of x raised to the nth power, we can just go ahead and plug it in. If we're going to raise a function to a power, we can plug it in first. We can evaluate f of a. We can do this limit first and then raise it to the power. This is kind of repetitive because it says if I have a polynomial function, I just plug in a. This says if I have a rational function or a quotient, I can plug in a. And then I have some roots down here for 11 and 12. If you need help with these or clarification, most of them, like I said, are common sense. Go ahead and put them down. They're supposed to help you identify or help you out in evaluating limits. I did put this list up on the website, so you have them there. If you don't want to copy them down, you can just go ahead and print out that list. The last of the properties, and I'll do a couple of examples as well, but the last of the properties is what we call the sandwich theorem. And on the sandwich theorem, what we're going to do is we're going to take the limit of a couple of functions, f of x and g of x, where that's going to help us evaluate the limit of h of x. What we're saying is that h of x has to fall between f of x and g of x for all values. And if the limit of f of x is L, and the limit of g of x is also L, if these are the same, then by the sandwich theorem, this has to be L. We're going to actually use this to prove some of the derivatives of our trig functions later on in the course. But let me do an example of that for you. Let's take a look at the limit, show you how you would apply this. Let's say I have something like this. The limit as x approaches 0 of x squared times the sine of 1 over x squared. I want to evaluate that limit. So what happens first of all, if I just take this middle part, if I forget all about this x squared existing, for example, and I just look at the sine of 1 over x squared, the sine of 1 over x squared has a minimum value of -1 and a maximum value of +1. Remember, those are the amplitude of the sine wave. That's the min and the max of the sine wave from last year in pre-calculus. If I now go ahead and multiply through by x squared everything, I get -x squared is less than or equal to x squared times the sine of 1 over x squared, which is less than or equal to x squared. And then if I take the limit of -x squared and +x squared as x approaches 0, they're going to be equal to each other. And they're both going to be 0. Since they're both 0, my conclusion can be the 3 dots in a triangle is therefore the limit as x approaches 0 of x squared times the sine of 1 over x squared has to equal 0 by the sandwich theorem. like I said, we're going to use this to derive, or we're going to use this to define some of our trig derivatives a little bit later on in the course. A couple things that people tend to have a little bit of difficulty with, let's take a look at. Let's say we have something like this. These are just different techniques of evaluating limits. Let's do first of all something like this. Let's say I had the limit as x approaches 2 of the square root of x minus the square root of 2 over x minus 2. And remember what I said in the first video, anytime you see a square root, anytime I see these square roots, I always want to think about conjugates. So what I want to do is I want to take and I want to multiply by the conjugate of the square roots, these guys right here, over themselves. And remember what conjugate means is I'm going to take the square root of x, but it's going to be plus the square root of 2. I just changed the sign from negative to positive. Square root of x plus the square root of 2. And when I do that, I want to multiply out the conjugates. And the reason why we multiply by conjugates is because the O and the I in FOIL will drop out. So I can go first times first and last times last. I don't want to multiply out the denominator because they're not conjugates. So it's the limit as x approaches 2. First times first is x. Last times last is minus 2. Oh, that's a beautiful thing right there. On the bottom, I just have what I started with. I don't have to do anything to simplify that. Now the x minus 2's will drop out. And what you did was you eliminated this discontinuity at 2. I have a 1 on top. I have a square root of x plus the square root of 2 on the bottom. And I can put in 2 right here for x. So I get 1 over the square root of 2 plus the square root of 2, which is 1 over 2 square root of 2. And don't worry about simplifying that. I know that, back in Algebra 2, geometry, stuff like that, we taught you to simplify those square roots. The AP exam will take any right answer, so just go ahead and leave it in this format. Lots of mistakes made algebraically in simplifying things like this. There's no reason to. Don't worry about it. Just leave it. I could make you simplify it, or I could try to get you to simplify it. If I give you a multiple choice question, we'll practice in that in class a little bit, but go ahead and leave it this way. This is fine. If you have trouble, like if you look at the answer key and you can't quite get the answer they have, it may not be that you've done anything wrong. It may be some simplifying that they do, because sometimes the simplifying gets really difficult. Calculus is not hard. It's the algebra and the pre-calculus that's hard. Let's look at a couple of other common mistakes I see. Let's take this one. Let's say I have the limit as x approaches 3 of x cubed minus 27 over x minus 3. Big problem here is people forget how to factor x cubed minus 27. Kind of on a side note, somewhere in your notes you should have this down. If you have a cubed minus b cubed, where a and b can be any perfect cubes, that's going to be a minus b times a squared plus ab plus b squared. And that's the situation I have right here. If I go ahead and apply that, I can factor this into x minus 3 times x squared plus 3x plus 9 over x minus 3. Now I can remove that discontinuity at 3 by canceling these. I can let x go to 3. I get 9 plus 9 plus 9, which is 27. So that limit is 27. The only thing that changes, only difference between whether this is negative or positive, if I have a cubed plus b cubed, that's equal to a plus b times a squared. Not plus, it's minus. Sorry. Minus ab plus b squared. So you are expected to know these. You are expected to know how to factor difference and sums of perfect cubes. And then one other example, just kind of going the other way, like this is something that we're going to do tons of a little bit later in the class. Say I have something like this, the limit as h approaches 0 of this difference quotient, which is what we looked at. Let's say I have something like x plus h squared minus x squared over h. This is the limit as h approaches 0, that difference quotient. That's going to be incredibly important in our next unit when we define our derivative, but right now we're just trying to get you to work it out algebraically. Again, the biggest mistake is people don't know how to square this binomial. So whether you know how the square pattern on the binomial or whether you have to write it down twice and FOIL it out, that's up to you. I think it's easiest if you know the square pattern. So it's going to be x squared plus 2xh plus h squared minus x squared over h. you are going to divide out an h, so everything that's only x, this x squared and x squared, these need to cancel, and they do. They subtract out. Now I can divide by h, and I get the limit as h approaches 0 of, it's going to be 2x plus h. I let h go to 0, and this becomes 2x. What you're going to find is that in our next unit, that's going to become the derivative of x squared. It's going to be a very important concept. But one of the things that, like, just go back to this x plus h squared, knowing the squared pattern. If you're trying to square a binomial, if I have a plus b or a minus b squared, it's a squared plus 2ab plus b squared. The only difference if that's minus is that's minus. That's the only difference between them. You also should know how to cube it. If you have a plus b cubed, it's a cubed plus 3a squared b plus 3ab squared plus b cubed. All this algebra 2 stuff that you need to know, all those formulas, and really, like I said, it's the algebra stuff that gets to be difficult. It's not necessarily the calculus or the limits. All right, well, best of luck. I'll clarify in class a little bit for you tomorrow, answer any questions you may have, and you'll be headed off into the next part of our limit stuff. And these limits become very important when we define our derivative. Good luck.